Good morning, everyone. Welcome to this security and encryption track. So I will indeed talk about some cryptographic functions based on Keccak, and everything I will say is actually joint work with my colleagues Guido, Johan, Michael, and Ronnie. So this is the outline of my presentation. I will start with some introduction. Then I will try to discuss the security properties of symmetric cryptography. Then the core of the presentation will be divided into two parts, the keyed applications and unkeyed applications, depending whether or not we need a secret key. Then I'll talk briefly about the Keccak code package and recap on the functions with some inventory. So the story somehow begins some years ago in the years 2004, 2005, when the most popular hash functions, MD5 and SHA-1, got severely broken. So at the time, there was also the SHA-2 hash function designed by NSA, but it was also based on the same design principles as MD5 and SHA-1. So at the time, there was fear that maybe these attacks would extend to SHA-2, and so NIST decided to create a new hash function called SHA-3, but not on their own. They would do that via an open competition. So between 2008 and 2012, there was indeed a SHA-3 competition. It was an open competition in the sense that every design was public. Everyone was forced to, of course, give the rationale of the design and give some open source implementation of it. And every team was allowed to try to break and try to attack any competing design. There was also some effort done to evaluate the performance of all these designs. It took the energy of quite a lot of the cryptographic community. A lot of teams from different companies and different universities took part of this competition. And you can see in this graph arrows going from the teams attacking the design of another team. So that was the situation in 2009. So our candidate was Keccak. So Keccak is a sponge function, which is somehow the generalization of a hash function. And it works like in this drawing. So there is a state which is initialized to 0, and then the input is cut into blocks. These blocks are processed one after the other. And between these blocks, there is this permutation F. So this permutation F, called Keccak F, is really the core of Keccak. It's really where the crypto is really happening, where most of the time is spent. So this Keccak F permutation is really let's say the common part of this presentation. Okay, so then in 2012, the contest ended with the announcement from NIST that Keccak was actually chosen as the winner of the SHA-3 competition. And 3 years later, it took actually 3 years for the NIST to publish the FIPS 202 standard with the SHA-3 hash functions, meant as a drop-in replacement for SHA-2 family of hash functions. But they also standardized extendable output function, ZOFs, called Shake 128 and Shake 256, so generalizing the concept of hash functions to an arbitrary output size. Well, in the meantime, before it was actually standardized by NIST, the 3GPP consortium published a new standard called TUAC, making use of Keccak internally for application in SIM cards. And then more recently, in December last year, the NIST published some new functions standardized based on Keccak in the special publications 800-185. And on the side of this standardization process, we actually worked on other variants of Keccak. So Ketia and Keccak are authenticated encryption schemes based on Keccak, which we submitted to the CSER competition. So the CSER competition is a currently ongoing competition for new authenticated encryption schemes. Last year, we proposed a new hash function called Kangaroo 12. And then recently, we are working on a new set of functions called Cravate. I will discuss these in a moment. So this presentation, the focus on this presentation is really on these new functions. So let me discuss the security properties. And so I want to show you is that in symmetric crypto, the security relies on two different parts. One part is the generic security, so the security of the mode, and the other is the security of the primitive. So to take Keccak as an example, the mode is the sponge construction. It tells you to initialize the state to 0. It tells you to cut the input into blocks to store them into the state. It tells you to apply the function f, and it tells you how to get the output. That's the mode. That's how it works on top of the permutation. And then, of course, there is a permutation. Can we say something about this construction? Yes. We can say something if we make abstraction of the permutations. If we replace this function f, this concrete permutation that you can implement in C or any language, you can replace it virtually by a random permutation. And if you do that, then you can start you can prove theorems about the security of the scheme when the function is replaced by a randomly chosen permutation. And you can even derive some theorems. This is a theorem that we proved at Eurocrypt 2008. Don't worry, I'm going to explain what it means. So first, let me go back one slide. So one important parameter of the sponge construction is the capacity, the value C that appears on the left side of this presentation, of this figure. So it's the size of the part of the state that is not directly touched by the input or the output blocks. And the security highly depends on this value. So what this theorem says is that if I replace, in Keccak, I replace the permutation by a random permutation, then the probability of some attack to be successful is upper bounded by n squared over 2 to the c plus 1, where n is the time spent by the adversary, and the time unit is the time needed to compute once the permutation f. So as long as this time n is much smaller than 2 to the c over 2, then this probability is negligible, and we have security of the mode of the sponge construction. So if we want to have, for instance, security at the level of 128 bits, then we need to take a capacity of at least 256 bits. But of course, this does not tell us anything when we replace this black permutation here by the concrete Keccak F. So the nice thing about these generic securities is that you can actually reduce the scope of cryptanalysis and focus only on the permutation, because what it tells you is that if there is a problem in Keccak, it should not come from the sponge construction, it should only come from the permutation. But the problem is that when you talk about the security of the permutation of the primitive, then there is no mathematical proof that it's secure. So the only way to gain some confidence is first to have some open design rationale of the permutation, and then have some cryptanalysis. And preferably peer review, meaning third-party cryptanalysis, and what's even better, a lot of cryptanalysis. Because if you want to build confidence, then you need to have some sustained cryptanalysis activity on the function, and the function, of course, not broken. That is the only way to actually have the security of most symmetric crypto primitives. So now let's discuss further with the Keccak F permutation. Most cryptographic primitives, and including the Keccak F permutation, is actually divided into rounds. So a round by itself is a very simple set of operations, and by itself it does not provide any security. But if you repeat this round many times, and enough times, then the security starts to build up. And there is a point where there are enough rounds for that permutation to be strong, and then in this case for Keccak to be secure. What people actually do when doing cryptanalysis is that they try to break 1 round, 2 rounds, and so on, and they see how far they can go. So the status for Keccak F is the following. Keccak F, the largest permutation, has 24 rounds. Keccak has been practically broken up to 5 rounds. The best attack on 5 rounds is a collision attack, published last year. If you allow complexities that are theoretical, so not having an explicit example, but an algorithm of complexity less than the expected complexity, then you can have collision attacks up to 6 rounds. And now if you allow any kind of attacks, then the best theoretical attacks are up to 9 rounds. But 9 rounds, in that case, it's time 2 to the power 256, which is a huge number. It's even higher than the number of particles in the universe, so that's really theoretical. So you can see from this figure that the 24 rounds of Keccak are actually rock-solid safety margin. Okay, so let me discuss some unkeyed applications. So the most obvious unkeyed application of Keccak is simply hashing. So a hash function, if I need to recall what it is simply a function that takes as input any string of bits of any size. So it can be a small message or a picture, a complete DVD, and then it processes it, and you get as output a digest of fixed size, 256 bits, for instance, which acts as kind of a fingerprint of the input. Obviously, the sponge construction can be used for that. The input is then your big file, and the output is your digest. Now, for the performance of the function, you can see that within the permutation F, there can be a lot of parallelism that you can exploit. But beyond that, you can see that the sponge construction by itself is quite serial. If you implement the permutation Keccak F on a Skylake CPU, you get about 1,100 cycles for one application of the permutation. If you now implement this permutation but using vector instructions by evaluating 4 different permutations in parallel, then the time grows slightly to 400 cycles. So per input byte, you can clearly see that it's more interesting to compute 4 permutations in parallel than just 1. So what can we do to exploit this kind of parallelism? We can do some tree hashing. So tree hashing is just taking the input, cutting it into pieces, and then evaluating the hash as a tree, where there should be a slide coming up, but my PC is a bit slow. Yes, here it is. So the message is cut into some pieces, and then each piece is hashed separately, and then the digests are then concatenated and hashed again to get the final hash. In the latest standard from NIST, there is this parallel hash function that exploits this kind of parallelism, and you can see that the number of cycles per byte, still on this Skylake processor, decreases significantly as soon as you can exploit this parallelism. As soon as your input is big enough, you can go down to 2.3 cycles per byte, so which is quite fast. So that's the existing standard. We can actually go further than this, and that's the purpose of this new Kangaroo 12 hash function. I've showed you that 24 rounds are rock solid. We can afford to decrease the safety margin a bit, and actually more than a bit. We can go down to 12 rounds and still have a comfortable safety margin, so that gives us a factor 2 speed up. And then we can have a special mode, a tree hash mode, that has what is called embarrassingly parallel, such that as soon as you have enough data as input, there is as much parallelism as your platform allows you to exploit. So concretely, what it means is that the input message is cut into chunks, and these chunks can be potentially hashed in parallel. So the more chunks you have, the more parallelism you can exploit, and the faster per byte it can go. The first chunk has a special status in the sense that the chaining values, so the intermediate digests that come from the other chunks, are hashed together with it. And that's something, a technique we called kangaroo hopping, and that's where the name kangaroo 12 comes from. All these values, 110, 110 star, and so on, come from Sakura coding, which we defined. And the idea is that as soon as we use Sakura coding, then generically we know that our mode is secure. So if there is no, it's proven that there is no problem on the mode side. If there is a mode, it has to come from the permutation reduced to 12 rounds. But the cryptanalysis that has been done on Keccak so far still applies to Kangaroo 12. So we rely on this, and we somehow inherit from all the cryptanalysis that has been done on Keccak and to apply it on Kangaroo 12. So concretely, still on this Skylake processor, if you have a short input, then the number of cycles per byte is 3.72. And as soon as you have enough input to fully exploit the parallelism, you can go down to 1.22. Yes, I forgot to mention that, so this idea of kangaroo hopping with the first chunk there used with the same hash function as the digest, the idea is that if your input is small, then there is no overhead due to the 3-hash mode. So this 3.72, it's really the speed for a short message as soon as there is one block, for instance. On the last line, you can see some figures for the Knight's Landing architecture. On that architecture, they have bigger vector spaces, bigger vector registers, up to 512 bits. So you can compute actually 8 permutations in parallel, and this decreases the number of cycles per byte below 1 cycle per byte, which is really, really fast. Okay, so now some keyed applications. And what I would like to do is, before I really speak about concurrent functions, I would like to take a step back and talk more abstractly about pseudo-random functions and what we can do with them, and yeah, what they can bring to us. So a pseudo-random function is a function that takes as input a secret key and some input string. Then it produces bits, as many as requested. From the point of view of the people who know the secret key, it's a deterministic function, meaning that anyone can compute it easily. But from the point of view of an adversary who doesn't know the key, then not knowing the key means that these bits, these output bits, they will look just like random bits, 50-50%, 1 or 0, all independent. That's what a good PRF should look like. So what can we do with such a PRF? We can build a stream cipher to do some encryption. So if you take the key and then give some input to your PRF, you can use the output as a key stream that you XOR with your plaintext. So if you do that, the ciphertext will look like garbage, and there is no way to recover the plaintext. The nonce there is some identifier, so that every time you use it, you use a different nonce, so that you get a different and independent key stream, and you can reuse the same key, the same long-term key. Okay, so that's for encryption, for confidentiality. A second application is authentication. So what you want to have is transmit a message in the clear, but have a way to make sure that this was not changed on the way. So you have maybe a client sending a message to a server, and the server wants to make sure that the message actually comes from the legitimate client. So what you can do is apply the PRF to the plaintext, your message, and you can use that output as a kind of a tag that you attach to your message. And you send the message in the clear plus the tag. The server is then able to really compute this tag, checks that it's correct, that it's matched. If it matches, that means that the plaintext was actually not changed. Now we can combine the two. You can use the PRF once to get some key stream. It means you can encrypt your plaintext into ciphertext. And then you use it a second time to have a tag over the ciphertext. And in that case, you achieve at the same time confidentiality and authentication. You have your ciphertext unreadable and a tag that protects against any changes that an adversary would try to do on the message on the way. Another thing that we want to achieve with a PRF is called incrementality. So let's assume that you want to authenticate some packets flowing from a client to a server. So first you have this first packet, you compute a tag over this first packet, and you send it. Then a second packet needs to be transmitted. Then what you want to have is a tag over the first two packets together, but you don't need to compute everything again. You just take the result of the computation with the first packet, and you extend it. You extend your computation with the second packet. Then the tag you get is a tag over the concatenation of packet 1 and packet 2. And you can go on like this. In this case, the final tag on packet 3 authenticates not only packet 3, but the actual sequence of packet 1, packet 2, packet 3. So there is no way that the adversary can reshuffle the packets, for instance. The tag then will not match. So there are at least two ways that we can instantiate this PRF to build schemes. The first one is essentially based on the sponge construction, and the second one is based on a new construction called farfalle. So let me first start with sponge-like constructions, and the first example is Keccak. So Keccak is an authenticated encryption scheme that we submitted to the Caesar competition. It uses the Keccak F permutation, but reduced to 12 rounds, like Kango 12. It works in sessions, so the idea is it really extends what I said in the previous slide. So the idea is to authenticate to encrypt and to authenticate the full session. So let's say that you start the session with some session key. It's called SUV because it needs to be secret and unique. So it can be a session key, meaning that it's different every time you open a new connection. It could also be a long-term key, but you adjoin to it some counter, some connection identifier that changes every time. Oops, sorry. So let's say you have your first plaintext P that comes in and some metadata A that you don't need to encrypt, but still you want to authenticate it. Then what you will get is some ciphertext from your plaintext and a tag covering both the plaintext and the metadata. Then you can go on with more plaintext and more metadata. Every time you get some ciphertext and a tag that authenticates all the session so far. And then maybe here in this last example, just some more metadata, maybe just a confirmation that does not need to be encrypted, but that is OK. And then the tag on this OK actually is an OK over the entire session, so including the context on which this OK is sent. So that's really useful in encrypting a network communication. Then we submitted a second proposal to the Caesar competition called Keccak. It's again based on Keccak, but it's sufficiently different from Keccak to deserve a separate submission and separate name. Keccak has less features than Keccak, but it's also simpler and targeted at lightweight applications like the Internet of Things, and you can instantiate it with smaller permutations, 400 and 200 bits, so that it can be really small in hardware or in embedded software. Then the second set of constructions I would like to talk about is really new. So it's based on the farfalle construction. So the farfalle construction is this figure. It resembles somehow a farfalle pasta, if you wish. So the idea here is that we try to exploit parallelism as much as we can. So on the left side, you have the secret key that is used every time, and then the input blocks. So your input message is cut into input blocks M0, M1, and so on. And all these blocks are processed to the permutation F in parallel. And the results are summed together. So this gives us the parallelism and the incrementality. Because if you have more input blocks that come in, you just need to add to the counter that you already have at this time. Then to get some output, you apply F again, and then some more Fs for each output blocks. So you can get an output of any size And again, if you want to have a long output, you want to do stream encryption, for instance, then all these output blocks can be computed in parallel if your platform allows you so. So this is the Farfalle construction, and Cravate is an instance using the Keccak F permutation, but with the number of rounds really reduced to not much. So typically what we expect now is to have 6 rounds, 4 rounds, and 4 rounds. So it means 14 rounds in total. If you remember the figure with 24 rounds, that was really rock solid. So 14 rounds between input and output, that's already quite safe. So now that we have this PRF, we can just apply them in a simple way, just as I explained in the beginning of this part of the presentation. We can build some concrete PRF to compute some MAC, some authentication code. We can have different flavors of authenticated encryption schemes. And I wish to point out the last one, which is a wide block cipher. So wide block cipher is simply an authenticated encryption scheme that doesn't have any expansion. So if you encrypt a block of a given size, then the output will be of the same size. And if you want to check the authenticity, then you need to rely either on the existing redundancy of your input, or if you really don't have that, you need to add some redundancy yourself beforehand. But it can be really interesting if you don't want to have any expansion, if you cannot afford to have a tag attached to your message. So concretely, if you encrypt with a wide block cipher a picture, and then at the decryption you get something which is really garbage, doesn't look like a picture, then you're sure that your message was tampered with. So any changes will diffuse completely over the full plaintext and your redundancy. So the fact that it was actually a picture, a meaningful picture, is destroyed completely. So it's all or nothing. So that's quite interesting. Okay, so that's all for the applications. Now let me give you some words about the Keccak code package. So the Keccak code package is simply an open source set of code implementing the Keccak function and all the variants that I've mentioned, except Cravate, which we are still tuning, and we hope to release it soon, this month, hopefully. So concretely, what can you do? First, the simplest way is to make a library. So you can just make libkeccak.8. And the prefix there, generic 64, 32, and so on, that's really the flavor of the implementation you wish to have. So generic 64 is simply generically optimized implementation for 64-bit platforms. Generic 32, the same, but for 32-bit platforms. And then you can have some more specific set of code for specific targets. If you don't want to have a library, just want to have the source files and to integrate them into your project, you just do the same but with .pack at the end, and it will create an archive with all the files that you need for a given target. Then there are some more things you can do. It comes with a complete set of unit tests, and you can run these unit tests with Keccak tests. You can say, I want this or that test. I want to have some speed measurements. You can do that from the command line. And of course, you can extend that in any way you wish. So let me give you some more details on how it's organized inside this Keccak code package. So the idea is that we have one layer above that is implementing the modes and the constructions in the more generic way. So there is no optimization, it's plain C code, it's portable code, and there is only one implementation. The idea here is really to make the life of the user easy, and there is nothing going on specifically for a specific target. Then there is this interface called state and permutation, and below which you can hide the details of an implementation of a given, of the permutation for a given platform, and it will do all the state management, so XORing bytes into it and applying, of course, the permutation. you can then easily substitute one implementation below SNP with another that is more optimized for your given platform, and everything above SNP will still work. Okay, so I will recap on what I mentioned before with some inventory. So for hash functions and extendable output functions, so the generalization of hash functions to any output size, we have some standard rock-solid instances, so the SHA-3 instances, the shake from FIPS 202, and then the generalization of shake with C-shake in the latest standard. So C-shake is like shake, except that you have an extra input, which is a customization string, and the advantage that you can have domain separation between different hash functions. So if you put a different customization string, you immediately get a new hash function with the output that is independent of C-shake with a different customization string. Tuple hash is also a generalization. The idea here is that the input is just not one string of bits, but it can be any number of strings. And of course, then the result will not depend just on the concatenation of all the inputs, but really on the exact sequence of inputs that you have. You can have a set of string and then give that as input to tuple hash. Parallel hash, I mentioned, is the tree hashing mode that has been standardized by NIST, and then can go 12, the faster version. Then something I didn't mention explicitly, but another useful unkeyed application of hash functions is the pseudo-random number generation. So the purpose of PRNG is if you have some random bits at the input, but these bits are not well balanced, maybe in this case, clearly there is a bias, and you want to turn that into a sequence of bits that really look random, uniformly distributed. Then the PRNG can do that. So in the Keccak code package, we also implemented Keccak PRG, which is based on our SAC 2011 proposal, and it has some extra features. If you have more seeds that come in, you can at any time add them so that they get mixed to the state, and then your output will depend on them. And the second feature is forward secrecy. So at any given time, you can say, okay, forget the past. And if your state is compromised, if let's say the PC is generating secret keys, and at some point the memory is recovered by an attack, then the attacker cannot go back this point. So it's irreversible and cannot find the secret keys that have been derived using this function before this irreversible operation. And authentication, there is Keccak, part of the SP 800-185. Of course, you could use HMAC with SHA-3, but that's really suboptimal, not a good idea. You can use Keccak, so Keccak is authenticated encryption, but you can use it also for simple MAC. And then this Cravate, a new construction, can be used also for authentication. And then authenticated encryption, of course, get your Keccak, and then all the flavors of Cravate that I mentioned earlier. And that's all I wanted to say, so if you have any questions, please feel free.
Hello. Hello, thank you for this talk. Yeah. I had some newbie questions about tree hashing. You mentioned here that parallel hash has been standardized during the competition, the SHA-3 competition. I was wondering if there is another mode coming up, because I remember some draft on the NIST mailing list about a specific tree hashing mode. And when you go to the website, to the Keccak website, there is a link with a paper describing the generic tree hashing and that new hashing mode that you may be building. So I was wondering where this is at, and also where Kangaroo 12, which is new to me, where this stands Is this also relevant to tree hashing with all the parallel things I saw in the slide? If you could clear that for me, thanks.
Okay, so as far as I know, only parallel hash has been standardized. It's true that we've worked on tree hashing for quite some time, and we proposed many different flavors of tree hashing. What has been standardized is just a subset of that, but of course, you can do any kind of tree hashing. If you use Sakura coding, then it's easy because then you can devise any tree topology that you like that fits well with your application, and then you're sure that the resulting function is secure. About Kangaroo 12, a design decision that we made is to have just one instance. So Kangaroo 12, there is no parameterization. The tree topology is fixed so that there is no choice. It's easier for the user. There is just one size fits all choice for Kangaroo 12. I don't know if it answers your questions.
How does it work with the lost bits? Every next iteration of the encryption depends on the previous one. So this is like a hashing algorithm. But if some bits are lost, I've seen this forward secrecy, or you can reseed it at any moment in time. But if some bits are lost of the ciphertext, does it to magically heal itself, like to decrypt the text?
I'm not sure I understood the question.
Okay, is there any... okay, you have the ciphertext, which is like ciphertext basically. But if some bits being lost with on the decryption
well, basically, if some parts of the ciphertext are lost, then you get desynchronized, and you cannot recover.
Okay.
There are ways to have some synchronous stream ciphers, but that's not the case of Keccak.
I believe AES encryption has been implemented in modern CPU architectures. Is the folding function of Keccak, is it possible to implement that? And is there any work in that regard?
So your question was about hardware implementations of Keccak, or?
Yes.
Okay. So I didn't mention this, but of course, Keccak was actually designed in a way that it can be extremely efficient in hardware. Either for a given size of circuit, it can be really fast, or it can consume less energy per bit than, well, let's say, than the other SHA-3 finalists. I don't know if it answers your question.
For instance, with the Bitcoin miners, ASICs for SHA-2 have been built. Is the same thing possible with Keccak?
Yeah, I suppose. I think, we didn't tailor Keccak for Bitcoin-like applications. Of course, in this case, if there will be a cost to do some mining, and I suppose that economically the threshold will automatically raise where the cost of electricity is at a given point is not economically interesting anymore. So that I think even if Keccak is more efficient in hardware for Bitcoin-like applications, it will not matter because the bar will be raised, and at some point it becomes economically not interesting to do more mining. But I'm not really familiar with Bitcoin, to be honest.
Are there plans to include Keccak with TLS?
I haven't followed TLS closely. I think TLS still uses a lot SHA-2. I don't know exactly why, but I hope that someday they switch to SHA-3 and not something designed by the NSA.
Thank you very much.